I often invite myself, and Michael is always incredibly kind in allowing me to do so. So, in fact, my voice is not great. Can you hear me at the back? Or is that a microphone that I should try and use?
We can hear you.
You can, okay. All right. If you can't, please complain. Okay. So, as Michael said, this is sort of, it's in some ways a kind of colloquium talk, which is it's about, thinking about a certain trend, but I'll phrase what I think is the trend and then describe some work that I've been doing, which has been motivated by thinking that way. So lots of people I've worked on with parts of it. Initially, I started thinking about kind of quantum games with Veer Bulsanani, Fiona Burnell. Chucha Lin is my graduate student, and then we've gone on to work with Frank Pullman. The last set of people are involved with using IBM quantum platforms and trying to do some. I'll describe exactly what on them. That's Andrew Daly's group at Oxford, and in between are various collaborators without whom I wouldn't have that much to say. Good. So, page down. All right, good. So while I was visiting Stanford, and during that time, we ran at Berkeley a meeting, which was the fifth of these meetings. The other ones had run at Oxford, called Quantum Interactive Dynamics. Our first talk was this preprint that maybe you've all seen, or if not, that just came out recently. We'd said the Shor's algorithm may be possible with as few as 10,000 qubits. If you've been following the game, this is down from 1 million, right? And if you're following the game, Atomic is a startup out of Caltech, which is going to use neutral atoms. You've all heard perhaps the Rydberg systems, right? And so, in essence, they're telling you that over the next decade, it's likely that these systems will succeed. They already can trap 6,000 qubits. They could get up to 10,000. And then within the decade, you might expect that, traditional cryptography will at long last be susceptible to actual attack using quantum devices. Okay. So these are the sorts of developments that are motivating what I have to say. The fact that there are hardware advances which are taking place, which are constantly improving. Obviously, large sums of money have gone into the industry, startups, and so on. So this program of building a quantum computer has led to the creation of these quantum platforms, which are unusual many-body systems because they have, even compared to their predecessors like cold atoms and two-dimensional electron gases or graphene, they promise to have a degree of addressability and flexibility which will be quite unique, right? You'll have very, very, very highly tunable systems. And if you have even 1,000 qubits and 1,000 gates that you can apply in layers of gates, that will be kind of a large space of potential quantum evolutions that will become possible, things that you will be able to do in a laboratory setting. And so the premise of the talk is that this future is coming, maybe in 5 years, if our atomic is right, even before they can do Shor's algorithm, they'll be able to do things on 1,000 qubits, which will be quite striking, and that this is a world we ought to be thinking about. So, in cartoon form, this is the premise of the talk, that we might cash the car, and then, like the dog, we'll have to ask ourselves, so now what? So I want to discuss now what. So the point of the first slide was to say that The future is not that far. It's really quite close. Okay, so when I finished my PhD in '92, right, this is what in sketch form quantum many-body physics looked like to me. So you first have to ask the question, did the Hamiltonian have a form? So whatever problem you were working on, was there a Hamiltonian that you could write down? This may sound funny to those of you who are young, but this was a big question in 1992. And actually, Kathy Lovin was here, she would recognize this. If the answer was that you had a Hamiltonian, you were working in the quantum Hall effect, and that's what I did. If the answer was no, that there was no generally agreed upon Hamiltonian in the field, you were working in the group rates. And again, for those of you who have some sense of history, otherwise it was kind of a version of King Lear in the group rates, but you'll have to figure out with the help of older people who was Lear and but that was the group rates. So I didn't have the fortitude to work without a Hamiltonian. So I worked in the Hall effect. By the way, this question, Tolle Larkin apparently used to ask at the Landau Institute, people will start and go blah, blah, blah. And Larkin will kind of look up and say, does the Hamiltonian have a form? So that was it. All right. If you had a Hamiltonian, you know, were you at zero temperature, on the ground state, low energy excitations, low temperature thermodynamics, correlations, linear response, quantum Boltzmann. Non-zero temperatures, obviously, these parts were easy, right? These were all part of the apparatus in many-body theory. Linear response was a problem. You know, you sort of lived and died on the imaginary axis, because that was some analytic continuation. It's a problem. And then, when possible, we were encouraged to take a continuum limit, and that as a quantum field theory. Again, back then, the fact that you could kind of do anything this way was in some ways somewhat surprising, because the quantum Hall effect had been discovered not so long ago. Thin liquids were in the air as objects of theoretical interest. And the fact that these would be shoehorned into topological quantum field theories, which to condensed matter physicists were, you know, very new, was actually quite surprising, because TQFTs aren't like regular field theories, right? They're logical. But so at that point, it was very striking that all of this would be done. And within 5 years of, you know, Anderson Murray. Now, of course, this is a caricature. Lots of other things were going on in condensed matter physics, but this is what the world looked like to me when I finished. Now, right around that time, right, I think two things happened. So one, in '95, there was DEC and cold atomic gases. And initially, you know, it just looked like, well, this is all weak coupling, those gases. This was all done in the 50s. What's the big deal? But as often with an experimental advance, the big deal ended up being that you could do new things with the experimental platform that you hadn't done before. So the entire field of non-equilibrium many-body quantum dynamics grew out of the fact that you could make these systems and then you could initialize them in very different initial states than you could ever hope to do with a solid in any degree of control, right? And once that happened, all sorts of theorists got interested in thinking in very specific ways about what it means to equilibrate, you know, how does dynamics work out in equilibrium, integrable systems, their thermodynamic, generalized Gibbs ensembles, eigenstate thermalizations, all sorts of stuff happened, many-body localization eventually, and so on, going out this week. Then, as you know, in '94, Peter Shor presented his algorithm, and then got everybody, you know, massively interested in now asking entirely new, questions of anybody, right? Which is, and then entanglement went from being something that was obsessed people working in quantum foundations to being something that everybody was interested in many degrees of freedom, and that's matter physicists, field theory generally. Like, hard to imagine today that entanglement wasn't something that everybody talked about, but that was true. So I like to summarize this sometimes in saying it's the JFK era in quantum. Now you ask not what you can do for quantum mechanics, but what quantum mechanics can do for you. Now, it's possible that those of you who've never read King Lear also find this reference puzzling, but this is the age of AI. You can just ask your AI system about God, and it will explain. Yeah, but to the older folks who've remembered JFK, I think you'll get the reference. Okay. The thing as you go through your career is you get from the older people not understanding your jokes to the younger people not understanding your jokes. Somewhere in the middle is a period when your audience gets you. All right. Now, lots have happened from 95 onwards, right? NEQ, tensor networks, entanglement entropy. And then perhaps most interestingly, even this, not most interestingly, but interestingly, quantum computational complexity ideas also started to be used in discussing physics. So that's kind of nice, which is to say, you start to think of computation itself as a quantum process, and then using computation to understand, right, quantum systems themselves in terms of their difficulty. So you can walk into a seminar today and find somebody talk about QMA hardness or whatever. You can argue about, how much value it adds for a given physics problem, but this sort of extended Church-Turing type ideology that any quantum system, right, is doing a computation, it's formally the same as a quantum computer. It's a nice, pleasing unification of the quantum universe, computation, understanding physical phenomena all at once. Okay, so what will many-body physics look like over the next 20 years, 10 to 20? So, obviously advances in quantum hardware, right, are there. And then meanwhile, we're getting lots of advances in classical computation. There's generative AI, which I mostly won't talk about, but even just machine learning huge amounts of data, right, and just finding patterns in it is something that's been happening for a while. So for concreteness, John Preskill has this term megaquarks, right? 1,000,000 quantum operations. So let's think of 1,000 qubits and imagine that you will have 1,000 layers of quantum gates in which essentially every qubit can be at once. And if that happens, you will have this capacity so just imagine each gate can be picked from a standard gate set. I'm not even complicating life by saying you measure something and you feedback, although that's important. Hence the term quantum interactive dynamics, which will interact with the system. But if you simply ask the question from a standard gate set, and if you had a megaquark device, how many independent circuits can you make? Right, just distinct circuits. Well, the answer is that, right, because it's a combinatorially large number, it just explodes. So we're making devices which in principle could make a staggering number of circuits. Now, most of them may end up looking like random matrices. In fact, they will, right? But nevertheless, the starting number is so large that it's interesting to ask what else is in there. A small number will be of interest to banks, something that will do an algorithm that banks care about or are commercially available. A small number will look like, problem of enzyme catalysis for some large, chemical molecule that other businesses care about. But there'll be lots left over. So there'll be this enormous haystack with all sorts of, individual sort of diamonds hiding in it, or, things that we'd be interested in because they're intellectually interesting. So the challenge to my mind is thinking ahead to the fact that these magical devices are coming. They will be able to make things. What will we do with them and how will we find these things, which are, sort of interesting. Now, I should say, this has already happened, right? So some years ago, almost a decade ago, I was involved in introducing flow-K phases. This was the case where you imagine circuits with many-body localization as well as other things. What was new here was it wasn't a Hamiltonian, right? It was a minimal step. Instead, you had a unitary, and then we talked about classifying unitaries and finding phases, defining phases. So this was still a relatively modest departure. There's been a lot of work focusing on the fact that you can make random unitary circuits. These have turned out to be the Ising model of thinking about quantum entanglement without any of the distractions of conserved quantities. So you can just focus on that. They've been enormously useful. They were also a good thing for Google to invent in their first experiment as, sampling from a random circuit being something that's difficult to do. So that was their claim of quantum supremacy. But from the physics viewpoint, they've kind of simplified a certain discussion of quantum statistical mechanics. More recently are these measurement transitions or monitored quantum circuit, where what you have is there's some process which is entangling, some process which is measuring, and depending on how frequently one or the other is done, right, you get a phase transition from a phase that has a volume law. But think about that. That phase transition, right, is very different from the phase transition we're used to, because you're actually going into the circuit and doing measurement. So it's now interactive dynamics. And it's something you wouldn't have thought of investigating if you weren't thinking of these quantum devices and what you're able to do. There's measurement of the criticality, state preparation, right? So there's a literature and more that's going on. So
So this stuff is already happening and accelerating. Okay.
So all of us should ask what else we might do. So I'll talk about two areas that I've been thinking about. The first of them will be a particular set of questions that I've been trying to think about with my collaborators. And the second part, the last part, will be somehow trying to search for things at one higher level of abstraction, which is what we call discovery mode. And so these are the two things I'll talk about, but obviously part of the purpose in giving talks this way is to encourage everybody to come up with even better ideas. Okay, so let me talk about quantum games. So what's a quantum game? Well, literally, right? It's the usual idea of a game, you know, except with quantum moves on a quantum board. So now, since I'm a many-body physicist, it will eventually need to be scalable in an n-qubit Hilbert space. I think those are the things that will be interesting to us. Now, there are different kinds of games. You could be, you know, players against the house, the Las Vegas model. So these are the games that actually first got me interested in thinking about these. So quantum foundations people, maybe you've all come across Merman's Magic Square game. There's something called the parity game. So these are all small numbers of qubits and games in which some team is playing against the house. And the idea is that if you have a quantum resource, some entangled state, you can win such a game with probability greater than the best classical strategy that you could have for winning that game, right? So there's something called the parity game. Google recently actually played it on their platform. In the list of 600 authors, you'll find Fiona Veer and myself, since we encouraged them to look at it. There's a question here which I don't have anything useful to say about today, but maybe some of you might be interested in. Would be the idea that maybe you could have some sort of classification of quantum states based on the idea that a given quantum state maybe helps you gain quantum advantage in some particular game, right? So as a kind of resource, maybe there's a classification topic there that somebody would be interested in. So this is players against the house. Then there can be players against each other, right? And so again, you could okay.
What would be the equivalence relation to such a classification?
It would be that all the states that give you quantum advantage for the same game would be equivalent. So they would, you know, so you define a particular. So in the way that works with a parity game is that, so the game is, for example, okay, I won't describe the game, but the GHZ state helps you win the game, right? So now you could ask. And one thing is clear is that the state needs to be a parity and state. So now the question is, if you deform it some, right? Is there a set of states which will help you win the same game, gain quantum advantage in the same game? Making sense?
A little bit.
Since I was
Okay, if you don't.
completely going to ignore it here.
Okay.
Yeah, but at the end, if you just, you give me, I can tell you what the warning evidence here. So. Actually, let me very quickly. It's a game in which you've got a bunch of players. The referee sends each player a binary bit. The players are an isolation. Their task is to add up their bits and divide by 2, and they've been given the promise that it's divisible by 2. All of it is base 2. So if these were real numbers, this would be nuts. There's no way you can add up numbers and divide by 2 if you haven't seen that. And of course, with binary numbers, you can just randomly guess and be half the time. So the issue is how much better than half can we do? So classically, you can agree in advance, if you see this, do that, and it turns out you can get 1/2 plus something which is exponentially smaller than. If you go sharing an entangled GHZ state, every player can do a local operation, send back the results from that, and that will effectively implement it. So now the question is, what's the full set of states that would allow you to do some local independent operation to allow you to win that game with probability bigger than the classical probability?
Okay, so then, you know, players could be playing, you know, against each other, and, you know, like chess or, now,
again, I want to take some of what's been going on and put it in the context of games. We could, right? So in measurement transitions, you can think of as two-player games. Player one tries to increase entanglement by acting on a bond picked at random with a randomly picked unitary. And meanwhile, player two tries to decrease entanglement by doing a measurement on some randomly picked site. So these are players acting at instructions from mission control, and these come in the form of random numbers. So the only real parameters, these are not strategic games, they're just doing stuff, and then the only parameter is the rate at which they get to try. And depending on how often they get to try, but one of them fits, right? So Frank Pullman, myself, and and Frank's group generalized to trivial case. We just said instead of measurement, what if one of the players gets to use a disentangle? But of course, this is not something you can imagine doing by measurement. This was kind of a theory exercise, and then you again get a transition, but there are aspects of the transition, which are somehow different. Okay. So let's come back to strategic games where there's something deliberate going on. So entanglement is tough, but measuring operators, right, should be a lot easier. And so one of the things I want to talk about is that if you start to think of games of deliberate strategy, much as we have the usual notion of equilibrium in the problems we know and love, systems and isolation, in games of strategy, and we know this from classical game theory, the new idea of an equilibrium that emerges is that of a Nash equilibrium. And so what I'd like to describe is, how that might be a notion that we want to use in thinking about quantum. But before I do that, let me just go back to just the business of error correction in a quantum lab, right? So it's a kind of partly random. You can think of it as a partly random game, which is to say the surroundings of your quantum device, nature, if you will, is doing something to destroy the quantum information that you're trying to store. Let's think of a memory. And in the case of error correction, you are allowed to do certain measurements, syndrome measurements, act based on that. And so it's kind of a contest, which you can think of as a game. If you were interested in what's the worst case analysis, right, then it actually would look like a two-player strategic game, because on the one side, you would deliberately pick the worst dephasing you could do. Right? And then on the other side, you would ask, can you get it? So you could imagine that game theoretic framework is actually the way you would calculate the worst case scenario for error correction given a code, given a certain syndrome. So I think my intuition is that with these quantum platforms, right, because we won't be wanting to do what we've traditionally done, right, which is to say, take some water, pour it in, let it settle down, stop shaking, equilibrates, and then we do weak measurements, right, which is go in and do scattering or linear response and so on. So our traditional view of life is there's a system that's largely there, and the purpose of the measurements we do is to reveal what's already there, right, and so on. So here, the thing is, error correction isn't revealing something that's there. It wouldn't, stuff you're trying to preserve wouldn't be there if it wasn't for the fact that you were actively, sort of error correcting. So with quantum devices, I'm not saying this is the only framework, but the only existing framework that I know that starts to approach how we is that of a game, that somehow we'll be constantly playing some sort of game, but there's probably a better way of formulating it. But it's so open systems is where physics has traditionally phrased it, which is to say you've got some environment, you've got a system, it's open, you've got steady states. But I think the fact that you are constantly going back and forth takes you beyond that framework, and so that's why I've settled on games. But again, I think that the broad question is one that everybody should, maybe think about in terms of.
But the notion of game implies discrete time dynamics. Is that something you're trying to emphasize, as opposed to some kind of continuous dynamics?
So certainly discreteness is important, because you do want to talk about player A, player B, as it were. But it's more that you are, you're kind of in constant dialogue with the device, right? And so it's error correction is a good example, right? So it's just. It's not observing. So the main thing I guess I want to say is not observing a system that's largely doing its own thing. You're often going to be doing things in which your dialogue And certainly at the microscopic level, it will be true. If you're not doing error correction at the bottom, you lose quantum information very rapidly. So I don't want to oversell it, but the sort of big thought in my head is it's somehow. Let me come back to this. Let me talk about Nash equilibrium, and then we can. Okay, so here's the next slide. So I didn't know much about Nash equilibria until I started to think about quantum game theory and use the term. So, but it's actually striking. It's a very trivially natural generalization of the kind of equilibrium we study in physics. So in physics, say we had 2 degrees of freedom. We generally have a function. It's the energy, it's the Hamiltonian, it's a free energy, right? We're always minimizing something. So we have 2 variables, a single function. We differentiate with respect to both, set it to 0. And then if you want stability, we have a certain condition. So 2 degrees of freedom, 2 conditions, and 1 auxiliary condition. The Nash equilibrium for 2 variables would be 2 independent functions, h1 and h2, and then similar looking equations, except that was h in both cases. This is h1 and this is h2. And this greater than 0 to less than 0 is the fact that economists and game theorists are maximizing payoffs, physicists are minimizing energies, but up to a minus sign, it's a thing. So observe that if you were starting in calculus, right, and you were asked to write down a 2 variable problem, this is kind of a very natural generalization, right, of what you would do. Likewise for them. Now, if you're doing economics, H1, is your restaurant, it's your profit function. Z1 is your price. H2 is my profit function, and Z2 is my price. The point is your profit depends on your price and my profit depends on my price and your price. But your detailed profit function and my detailed profit function are different. Maybe you're selling Chinese food and I'm selling Indian food, right? And maybe we're in different neighborhoods. So in other words, our cost structures are different. But nevertheless, in a common market, we are sensitive to each other. And in the Nash equilibrium, right, I would have maximized my profit and you would have maximized your profit, subject to the fact that the other person exists, right? And that's very important because that keeps us from making as much money as we like because, people can go elsewhere. That kind of. But mathematically, it's as simple as that. What's striking is in physics, we almost never do this, but we do this all the time, right? And that's because this sort of stuff comes naturally when somehow there's something agentic. There are players or agents, which are somehow trying to have, incommensurate objectives.
Relative to the left-hand side, the right-hand side looks rather underspecified in that you're only taking partial derivatives of 2 separate functions. The kind of solutions you'd find would be much more numerous.
And that's also correct, which is to say there are typically multiple Nash equilibria. That's exactly right. As you know from visiting different universities, each one is unhappy in its own way. But you're absolutely right. Okay. So in social phenomena, that actually is an insight, right? Which is to say, why are you stuck? Because you only get to control one variable, you don't get to control the other one. And that's why, but nevertheless, it's a powerful insight. It tells you why you're stuck. Okay. So then strategic games, you could, say, well, there are some simultaneous and some sequential. So let's maybe look at those. So here's an example of a simultaneous game, right? So that's prisoner's dilemma, but it's a bit like taking part in an auction. Maybe, you're both bidding on the same house. So prisoner's dilemma, as you don't think about actual prisoners, that's not important. There are 2 players who are going to submit binary number bids, which are 0 or 1. And this is the so-called payoff matrix. If both submit 0 bids, they get 3 each. Both submit 1, they get 1 each. But if it's 0-1, then one of them wins big. If it's 1-0, the other one, right, wins big. So famously, what happens is, even though this would be the cooperative solution, right? You both get 3. But the trouble is, if you're there, both of them have an incentive to try and change their bid, because they would get 5 and the other person would end up with 0. And so they both move away from it and they end up here, which is where their take is the lowest. In the prisoner's case, they're supposed to inform on their friend and end up with a longer sentence. But in this case, it's just fail. Okay. So that's the Nash equilibrium. And the point is that neither player benefits by unilaterally deviating from them. They would have to decide to collude and agree, but if they don't, then they would end up there.
Good. So I want to quantize this system, right? So how do I do that?
So first, these were the classical functions. I will define two quantum operators in this trivial sense that each Z1, Z2 is a quantum state, right? Diagonal state, and I just multiply, I take the projector onto the state and multiply it by the value of this function for that state. Now I can view the game as a sequence of operations. I've got, let's say, the inputs, there's an input state that's handed to the player, which is the product state 1. Player 1 is allowed to act on it with 1 or flip it, 2 or flip it with the Pauli X. Out comes this, the referee measures it, calculates the expectation values of these, and then declares the outcome, right? So now we can generalize this and say, okay, I had an initial state. Let me allow it to be a general 2-qubit quantum state. Let each player act on their qubit with a single site unitary with some outgoing state, and let's measure the expectation values of the same operators that I had, right? So of course, these operators are special, they are commuting payoffs, but commuting Hamiltonians, projectors, are a big industry in our field and have turned out to tell you things. So I think one should not hold against operators if they commute, if they commute. Okay. This is just to show you that, we've developed, some mathematics and thinking about it. So for instance, this particular problem, it turns out you only need real coefficients. So the most general state looks like that, which, because it's 4 numbers, that's, square to square and sum to 1, means you could represent all those states in a 3-dimensional, in R3. You can ask for Nash equilibria to linear order. So and those we call Nash states. So there's interesting geometry. So the red lines, including the blue stuff on top of it, the red curves, form an algebraic variety, which you can call the Nash variety, which is the locus of linear stability. And then, exactly as you said, the Nash equilibria, there are lots of them. So those are the blue ones. They're not the full set, but they exist. Good. In fact, for the 2-qubit case of this problem, for each value of 2-qubit entanglement, you get a Nash equilibrium. So remember, what you have a state, and you're kind of allowing. It's like one single qubit. So it's like U2 tensor U2, because you can act on each qubit independently. So these are orbits of a given state in the full Hilbert space, and you're looking on those to see if there's a Nash equilibrium. And so for maximally entangled states, the payoffs are the biggest each. This, by the way, just looks like superposing the two cases where one does badly and the other does really well, right? So this is why you don't think about prisoners, because you find yourself asking questions like, why would a prisoner never sign up for this, right? And don't ask that question. Just think about the new question. And then you can extend this to many player games, which I'm mentioning just because it generates, a technical question. I won't go into this, but you can make lattices, you can make graphs, which starts to look like, yeah.
So this 5 has it's like 5.
It's 0, 5, and 5, 0. It's a superposition of those, so the average is 5 passes.
So there's no equilibrium that makes both players cooperate in this case.
But this does, in the numbers I showed, this does, yeah, correct.
So it does better than defect game, but not as good as. But that's a numbers thing.
Yeah, it's a question of whether it's a Nash equilibrium or not. Yeah. Obviously, the payoffs would be better exactly the rule, but we're asking the question: is it stable to small deviations? Yeah. Right. Okay, so you can, you need to do, these are examples of non-reciprocal interactions, as it were, because if you have 0, 1 or 1, 0, you get different outcomes, and so there are interesting, many body problems of finding such Nash equilibria, which we're working on, but I won't. In the interest of time, let me actually not describe some of this stuff to you, and maybe just move on. But please ask at the end if that's interesting. Okay, let me make one connection to physics, which is that one can make a connection between a certain kind of metastability in physics and the idea of the Nash equilibrium. So let's imagine I have a Hamiltonian, which is the sum of local terms, and these local terms are ultra-local, right? So there are no tails. They are strictly of compact support. So many of our favorite models. So we know the following. So it's now what we'll do is the following. We will define a subregion A of our larger system, and we will allow unitary operations on that subregion. And we will say that a state psi is metastable if operations unitaries on region A do not decrease the expectation value of the Hamiltonian on the entire system, right? Because now we're doing physics, there's only one Hamiltonian. So I'm not, on the face of it, I'm not asking the Nash question. The Nash question was, player A does a unitary on their qubits, does the expectation value of their payoff function, right, go down or not? Here I want to do physics, so the only thing I'm interested in is, does the global energy go down or go up? But nevertheless, I can do the following. What I can do is I can divide up my system into boxes of size A, and I can collect the terms which live strictly within A and the terms that straddle the border of A, combine them into something which I'll call the payoff operator related to this particular region A. And now you can convince yourself that if all I do is a unitary in region A, then, so let's say if this is, right, so imagine, for instance, that this is the ground state, then what you would find is that if you did a unitary in region A, the only terms in the Hamiltonian that could be affected are the ones that are collected here, right? Because everybody else is just outside where I'm acting. And so the rise in the expectation value of the full Hamiltonian, the change, is captured already by restricting to thinking about what happens to the expectation value of this operator, right? So the stability of the ground state would also be stability of this local, payoff operator. And in general, you can lift this idea and find that using this is the same as specifying that. So it's an idea of metastability, which is not quite how you would use it in physics, because there you are also thinking dynamics, can the system tunnel, can the system activate over a free energy barrier? But nevertheless, it's a version of what you could think of as defining, metastability, even if it's not dynamical, it's a kind of kinematical metastability. And that actually does look exactly like the international.
So the players here would be applying these operators.
Correct. Players will be attacking applying unitaries. So you're sitting here, you're allowed to act on a unitary here, and the resulting state will have an energy. If the state is metastable, then the resulting state will have higher, or the energy will not go down. And that statement for the full energy will be the same as saying that if this was your payoff operator, your local payoff operator, its expectation value also did not go down. So you can relate so the main thing was to somehow take the full Hamiltonian and make sure that the local payoff operator had the terms from the full Hamiltonian that care about the unitary that you're going to apply.
In the classical prisoner's dilemma, there's kind of a distinction between, like, say, like a one round versus multi-round, where in one round.
So this is why I don't want to go down this path.
Okay.
No, and so these are all excellent questions, which is to say, in game theory, the question is, these are supposed to be rational players. Who's a rational player? Why would they do this? Right? So there's evolutionary game theory. The players played against each other a lot, maybe they would converge on the strategy and so on and so forth. These are all good questions. I actually really do. Right now, I'm mostly urging this on two grounds. One, the notion, general idea that you end up talking to your quantum devices a lot, and so maybe this is a useful framework. Second is, look, it's a new family of equilibrium problems. If you're happy finding eigenstates and Hamiltonians, this is, and there are even more of them, there are all sorts of Nash equilibria. So as of today, I would say, well, here's an interesting set of questions we could ask. Quantum devices will be potentially a good place to ask these questions, and so we should ask them. But everything else you say. So there are two independent motivations. One is closer to why you might want to do it. The second is it's there. And you can't really complain because we're making these devices anyway. So we have to figure out what to do. Yeah, right. All right. So that was a physics digression. So sequential games like tic-tac-toe and chess, by the way, they also have Nash equilibria. Chess has a Nash equilibrium that no one knows. We don't know, for example, maybe in the Nash equilibrium, white always wins, or maybe in the Nash equilibrium, black always wins. That would be the perfect pattern of play in which no player would want to deviate, right? So despite all their massive advances, deep minds have not found the Nash equilibrium for chess. What they simply have is a program that does a much better job of trying the best possible strategy than any of us, right? So that's because the game is too complex. But tic-tac-toe, I think you all know the chess Nash equilibrium, right? And then after all, you know exactly what to do. All right. So we're going to quantize this now by allowing for superpositions of moves. So you will not only move your pawn from here to there, you're allowed to put it in a superposition of stuff. But then we have to project at each stage, which is to say, you know, it shouldn't be that I make a superposition on, you know, which includes this particular square, and then Michael makes a move with a superposition that also includes that particular square, because we want to keep the same rules of the game. So we will project out the possibility that we have both tried to, you know, put pieces in the same square, as opposed to taking pieces. So you need that kind of stuff. So that looks a bit like gauge invariant states. And now the new feature of quantum games will be that if I'm allowed to make superposition moves, right? It could be that the best strategy relies on my winning because there were two different ways of getting to the same end state. There was an interference phenomenon. So that's the new aspect of these games from a sort of quantum viewpoint. All right, so I'm going to give a really stupid example, which is one-dimensional tic-tac-toe. So what is one-dimensional tic-tac-toe? Both players put down the same symbol, right? And then the first one who can finish a row of 3 wins, 3 contiguous ones. So player 1 is going to go here. Player 2 can go here, can go there, go anywhere, but player 1 is guaranteed to win because they just finish him, right? Either in between or from between. Now, supposing we examine the stability of this Nash equilibrium to player B going quantum, being willing to do superposition. So now what happens is player B can decide to superpose between these two, right? Now player A, who's still plodding along classically, will either try and hit this one or will hit that one, right? But half the time, they would not have succeeded in winning. Half the time, the game will still be undecided. So in this simple sense, player B destabilizes the classical Nash equilibrium by going quantum. Now you can ask, what if player A went quantum? And the answer is actually, it doesn't recover things. So in other words, player A was very happy in a classical universe, but in player B has gained a relative quantum advantage in the quantum case, in the sense that they still lose, but not as badly as they used to. Right? No. So obviously, I would have liked to have presented to you what happens for the tic-tac-toe you're familiar with. But right now, we're trying to find these Nash equilibria working on classical computers where each superposition, right, has to be represented in some large Hilbert space. So for instance, there are 9 squares, and it's a superposition of 9, right? It's even if it's just real numbers, it's R9. And so the algorithms for searching look like playing continuous variable classical games and are computationally sort of difficult. We have done some work in which we restrict the superpositions for the 2-dimensional case, and we can see that going quantum again destabilizes the classical equilibrium. The hope here again would be that when we have quantum devices, we can work out such optimal strategies much more efficiently, because the quantum primitive would be done in the quantum device, and the classical optimization is something that you would do in dialogue with the quantum device. Okay, so I think I said all of that, so I will skip it. So one way of thinking about games is this is, you know, the starting position of the chessboard. You go there, depending on moves. Then the second player does something. So potentially you can imagine ending up in the same position by 2 different routes, because, you know, player A moved this pawn, player B, you know, kind of depending on sequence. And so once you see a graph like this, you can, you know, think to yourself, yes, I could get interference between this trajectory and that trajectory to a final end state. And so it's impossible. The question is, do Nash equilibria use this kind of interference? And in this particular case, we can again write down, you know, proofs of principle, model payoffs, and so on, where you can see that happens. Okay. All right. Now for something not completely different, but actually more general, but also more detailed. So far it was this idea of playing quantum physics, right? And the idea that quantum computers finding Nash equilibria, playing quantum games would be something that we can do. Now the discovery mode idea is the following. I've got all these circuits, right? Where are the interesting ones? So one approach could be that you try and decide a bit in advance what interesting means. What would you like the circuit to do? Would you like its eigenvalues to have certain properties? Would you like its eigenfunctions to have certain properties? Maybe you want it to start with some number of initial states and produce some final outcome. Something that causes the circuit to be interesting. So if you can define an interest function on the space of unitaries, then you want to estimate the interest function on a quantum computer by running that circuit some number of times, doing some number of measurements. And then you want to do classical optimization in the space of circuit. So you go in and you change that particular one, you see whether the interest function went up or down. An interest function is the same thing as a cost function or a loss function, except those two have negative connotations. Here we really want to say that something is interesting, but it's the same thing. So that's what you want to do with your classical computering dialogue with the function. So that's the general idea. There's some circuit, there's some function of the space of unitaries, you estimate it, and then you change the circuit parameters, go back, measure it again, and then in this feedback you find, hopefully your interest function has some noise and it grows, and eventually you get to a value where it's significant, and then you say, aha, I found it in some circuit. Right? Okay. So what we've done so far is simply look where we knew what to find. So we wanted to rediscover some things that we thought we knew existed. So we started with time crystals. If we had never heard of time crystals, could we find the unitary circuit that that produces a time crystal behavior by simply requiring that the time dependence of a Floquet circuit should have twice the period of the Floquet circuit itself, which is what the rating of discrete time translation symmetry is about. So as I said, in this program, the challenges are finding interest functions, then also figuring out how to collect data efficiently to estimate them. Then search strategies, which include optimizers, but also maybe circuit classes that we might want to restrict. So in the paper on this that we wrote, we've used some of these techniques that people at Caltech have been very good at coming up with, classical shadows, kernel PCA, as ways of finding things. And then we've also done some implementation on IBM's hardware up to 26 qubits. Okay. So
Can
yeah,
you give some great example of each?
Yeah, I'm just coming to it. Good. So here's for instance for the time.
So what do? We start with a random product state, some number of qubits. There's some unitary which is currently being implemented in your circuit, right? So you act with this for some number of times. So the business with time crystals is you act with the unitary, the system settles down, and after a certain time, basically the state repeats every 2 periods. So let's say if you had all through up, what's going to happen after a while is you get up and down and up and down and up and down successively. That's the time crystal, right? What's interesting is that there are such unitaries that do this sort of thing very robustly. So we're going to collect these late time states. We'll leave out some transient, collect some states. Okay, classical shadows. The thing is, even on a quantum computer, right, you can only measure so many things. Everything is exponential. So it's very important to have efficient ways of collecting data, storing it, analyzing it, right? So classical shadows do that, right? And then, so this is what the topic which is also called unsupervised learning. If I just give you a bunch of data in some space, the simplest unsupervised learning problem is does it break up into clusters? Are there distinct blobs of things? So in the time crystal case, we're trying to ask, I have these states, do the states break up into 2 blobs? One of them having to do with even times, the other having to do with odd times. Okay. So that's the Now, I have to define an interest function, which has to be a number that's going to optimize it, but that's the classification task, right, that I'm trying to solve. So this, we have the shadow kernels, then there's a PCA, which is basically principal component analysis. And then you pick a couple of, some number of eigenvalues. I'll just show you pictures in a minute. So you end up in a space maybe which is 2-dimensional, 3-dimensional, 4-dimensional. Now you've got points in a space, and then you can run these clustering algorithms. So there's something called part in which you have different points, and you say, first you pick the points which are closest to each other, collapse them, then you repeat and repeat.
So, okay, so don't read this in too much detail, but here are some pictures.
So these are two principal components coming out of this analysis using shadow density matrices and so on. The sort of thing you're looking for is, do they kind of all cluster together? This is the trivial phase. Do they break up into two blobs? Because that's the time crystal. And then when you have blobs, the way you analyze them is that you look through at step one and you find the ones which are closest and you declare them to be a single point, likewise so on and so forth. Then you repeat and you repeat and repeat. And if at the last, then you look at the height of this increase in this clustering distance at the last step. And the reason is, at the last step, if you have two clusters, these guys all collapse to a point, all collapse to a point, and so you get a very big. If you did the same thing up here, right, you wouldn't get that. So this is kind of not interesting because in each step of clustering, you don't get a big gain. And if you do get a big gain, then you know you have clusters. So this is kind of standard technology for finding a set of points in a high dimensional space and deciding whether they're clustered. Right? So what we've done is we've taken a question of classifying these quantum states into a set of points in a high dimensional space by doing shadow measurements, using PCA technology to find principal components and so on. Then there's other stuff I'm not telling you about. So that's the function we are seeking to max. So here are examples of runs on a classical computer in which you try and iteratively modify your circuit. Sometimes it doesn't work, but many times it does. And you find that the value looks a lot like the thing you sketched at the start. Right? And we've done the same thing on a quantum device, which is this picture. This is for 12 qubits on an IBM machine. And you can see the optimizing actually worked
rather well in that case.
How does the update work? So it's a big space, right? Of theories. How do you choose which direction?
Very good, excellent question. So right now, we're not, okay, so we have looked in a restricted space. So we're looking where the number answer, okay? So I can, if I didn't, did I have it on the previous slide or do I have it in the next one? So here, for example, we've looked at a uniform average field and a uniform average J plus noise, right? Now, what we'd like to do, and which is what we're working on now, is to start with far fewer assumptions. Now, the full space of unitary is in us. So of course, if you just decided to work on a 1,000 qubits, you're luck, right? So I think part of the business of learning how to do this will have to be some idea that you start on small systems, right? Start with some insight to find something that gives you some sense of what the interesting parameters are. Then you use those to seed the next system up, and then you make your way up. So we're currently trying an experiment of. So I'd like to be able to basically start with a randomly picked unitary, find something, and then make my way up. That's not what we've done right now. So the so-called barren plateau problem and so on, right? All of these are functions which are very flat, you may find it difficult, so on. But again, the thing I want to say is classical optimization, it may be a pain in the neck, but if there's one thing we've learned from large language models, optimization, classical systems, it works strikingly well. If you put enough money and people behind it, people find all sorts of tricks. So I don't view that as a real problem. I think there's going to be a lot of creativity involved in. So the analogy I sometimes like to give is, look, supposing somebody had handed you CERN in 1930, right? You have this enormous machine which does these experiments, staggering amounts of data coming up, right? How would you discover particle physics? That's not how it is. We went step by step, small machines, few particles, bigger. But if somebody had handed you the whole thing, right? So a 1,000 qubit machine, right, is going to be like that. You have a discern from anyone in physics, and some ways there are all sorts of stuff that you produce. So back in the 1930s with CERN, you would have had to just close your eyes to all sorts of things and try and figure out what were the most striking things, right? So I think we'll have to
learn how to navigate our way, but absolutely. It will not be a blind activity. So I think there will be many body interest function designers. These are the jobs of the future, like social media influencers. So you should prepare for them now. Yeah. Okay, good. Thank you. Perfect. All right. This one was more, and maybe the people in the audience who will be better at this than me, trying to mimic the idea of writing a Landau theory, right? So I've got some space of unitaries. What are natural functions to write? Somehow in terms of some basis functions, then maybe trying to make up a polynomial. So we had the thought, well, let's just take powers of unitary and take a trace, right? So that gives you some structural eigenvalues. And then you would create interest functions by, taking sort of, you take these powers and then you take a function of it with a coefficient. So what you realize when you do this is that if you could, for instance, pick all positive coefficients, and that would drive you towards rediscovering these dual unitary circuits, because it would tend to want you to have the spectrum form factor to be as linear as possible. So we didn't start off wanting to rediscover them, but our first guess at trying to write some Landau factor. For those of you who mathematically, have a better, anybody who knows how to walk around, the unitary group of size 2 to the 1000 should try their hand at it, right? I mean, there must be some way of thinking about which members of the unitary group are somehow interesting by some criterion. And I think finding interest functions that somehow bias you in that direction would be interesting. All right. So I think I already said this. We're thinking about aspects of quantum codes where one of the issues is finding, these complex quantum codes, good quantum codes, so on and so forth. Finding logical operators, right, which move you inside the ground state. You can often find in the code, but finding explicit practical logical operators can be an issue. Right now, Professor Kanti is visiting, he's been doing classical optimization and finding logical operators. But the hope would be that, hope from my point of view, is that maybe for 100 qubit quantum codes, we won't be able to do it in a classical machine, maybe, and then, but maybe we'll be able to do the optimization on quantum hardware. Right. So, and then stepping up in system size. Okay, so all these themes were sort of pulled from all these papers, which you have to read. I should mention that there is an older literature on simultaneous game. That's not where I began. I started thinking about non-local games. Then I had a book from my old Princeton colleague, the game theorist Avinash Dixit's undergraduate book. So I just started opening that and said to my graduate student, wouldn't it be nice if we could quantize this? At some stage, somebody must have thought of this. And in fact, David Fire began talking about quantum games back then. The Nash equilibrium doesn't seem to have shown up very, very broadly, but nevertheless, people were thinking about these things a while back, and then the subject seems to have gone into hibernation. All right, so to close, so I think quantum platforms can certainly be used for computation, for simulation, but I think they will also reshape what we mean by many body physics. We could play games with them. We could use them in discovery mode to find some unitaries or maybe circuits of feedback, but no doubt there are other things. Now, a question, of course, that has come up, maybe not for this particular audience, that you've all been pretty chill with everything I've been saying. Is it physics or is it experimental mathematics? So what I generally said, it's not something I just made up for this talk. I've been saying for a while. I think physics is largely not a natural science, right? If by natural science you mean you go out and you say, why is that blue? Why is that star shining? All of that stuff was done, right? Relativistic, quark-gluon plasmons are things we create deliberately, cold atomic gases, 2DEGs, right? Even particles. So in other words, a lot of physics is making special circumstances and then, checking your understanding, kind of combinatorial results from physics to combine various ideas of physics and predict some news. So maybe it's experimental mathematics, which is to say maybe what will happen is we'll play with these devices and discover. And probably some of it, no physical device is ever going to give you infinite accuracy answers, right? So you'll find something interesting and then maybe you'll sit down and maybe the generative AI model, maybe the ChatGPT 17. I can't promise you that human physicists will be doing all of this. It could be a physicist, but that's a separate talk. But nevertheless, they could be incredibly powerful at that. Now, physics, quantum physics on some number of qubits is the space of unitary evolution, right? That's what quantum mechanics is. So it's also physics. It's also experimental mathematics. And in any case, we're building these 10 devices, so might as well get the most out of them. Thank you.
So for these Nash, quantum Nash states, this was like some 2-qubit state that you mentioned, like it'd be nice to consider the into some version.
Right.
So were there like,
So for the particular prisoner's dilemma, we have looked at larger, so you have to put these arrows because it's non-reciprocal, but you can pick particular combinations. Yeah. Each player is the right sees, So we've looked. So we look for Nash equilibria the following way. We pick a state. So we've been looking at low entanglement states for the most part, although we have evidence from small system studies that even high entanglement states probably are not going to give us something new. So we pick a state, then we look on its orbit. So the orbit being, we search over applying single qubit unitaries to each layer of cyberspace. In the simplest cases, we're taking each qubit to belong to a plane. We find a Nash equilibrium. Great. Now we want to find another one, or if we don't find one. So then we apply an entangling unitary, let's say 2 qubits, which moves us to a different orbit than we search on that. So this is what we do in the classical computer, and we have some evidence that this particular GHZ class, it's a more complex story for the reasons that were brought up. There are many more Nash equilibria, right? Now, the way I described it to you, this is something we could easily do in a quantum computer. Like qubit unitaries. So searching for Nash equilibria on a quantum computer, right, should be an activity we should do that. I personally think, it would be nice if instead of having to go through Google and and so on, you just had something sitting in the next room. By the time we're up to 1,000 qubits, 1,000 gates, I mean, it's something. It may well be an activity that actually primarily becomes an academic activity because I don't think Google's stock price will care very much if you find an interesting unitary, but we could end up with devices that really. So I'm hoping that this is something that will kind of be in-house, so you can just play with it all day long and sort of fun things.
A question. I have a question, which is, maybe it applies as well to classical games, but are there physical systems which kind of, you made the analogy between Nash equilibrium, typical thermodynamic equilibrium or metastability. Are there physical systems that somehow naturally go to something that can be interpreted as a Nash?
So metastability was my example, and that a definition of metastability you could think of as a Nash equilibrium. So that's why I suggested that. Now, more generally, it's an interesting thing, not typically in physics, right? And it's a good question, why not? So you're in a good company, Bob Laughlin was asking this one. So let me give you a word, which is, of course, we're all highly cited states, the standard model, right? We're all in agreement, each one of us, right? Yes. One of the things I've discovered with the coming of AI is that while every physicist is supposed to believe this, but in fact, most physicists went around with the belief that they were somehow an exception to this rule, right? But we're discovering it's not true. It's atoms all the way down. But anyway, you and I can play a game. So certainly sufficiently complex physical systems are capable of playing games. The question is, and within physics, what's this, if you scale down the complexity, what's the level at which you can imagine relatively simple physical systems which you can model for long enough periods of time as effectively playing it? I don't know the answer to it, but we should be able to get down quite a bit from the human level to so interspecies models, things like that. Those are, so the typical one tends to be a case where there's a well identifiable agent pursuing objectives. But I think that the interesting question is there a mean field sense in which you would describe a more complex physical system as being divided into agents and substrate and subunits, right? So we haven't looked that way, right? And so on, but I think that's something we could think about. There's a related example, a bit off to a side, so quantum information people sometimes like to bring up LOCC, right? Local operator classical communication. And your old colleague, Shinsei, I think is absolutely trying to classify using LOCC. Now, the question is, if you wanted to classify, materials, there's no one inside a cuprate, right, sitting there making phone calls across the sample. There's no classical communication. You might say that's kind of irrelevant. But you can imagine physical systems in which some degrees of freedom are very quantum. Some degrees of freedom, maybe phonons or something, are very classical. And somehow something happens here which you could interpret as a classical communication going across. So I think with these sorts of things where you invoke agentic Alice and Bob chess players, I think it's the question we should ask. Okay, can we get that as a kind of effective mean field behavior in settings that don't immediately have problems? Okay, that's my rant.
Other questions? All right, let's thank Shivaji again.
You know about Andreev's semi-quantum liquids? I can't really think of that.
No, I don't. What's that? Oh, is this the, but that's related to
It's
stuff we were telling about,